Hi, welcome to 13th session on group theory. This is the third session on cyclic groups of and order of an element. Mostly we will be dealing with only order of an element. There are few interesting results which are very much used in algebra later on. So I would like to talk about certain things. And if you are a BSc student, probably you may not need it, but learning them doesn't hurt. In fact, it will make you much more comfortable. Okay, so let us start with an example. The first question we want to deal with is, suppose G is a group and A and B are two elements of the group. Okay, assume that both the orders of A and B both are finite. Okay, then we have the group product AB, similarly BA. So what will be our guess? A natural guess will be AB will also be finite order. Okay, unfortunately that's not true. Okay, so we will give an example. Then the next question we will ask is, suppose A and B commute, right? And suppose order of A is m, order of B is n, and AB equal to BA, then AB to the power mn will be A to the power mn and B to the power mn, that is identity. Therefore, if they commute, then the AB is of finite order. Its order will be at most m times n. Is that clear? So let us get started. So G is a group. Okay, maybe I'll shift. Okay, and A and B are elements here. Okay, and order of A is finite. Order of B is finite. Question is, order of AB, is it finite? This is a question. We are not claiming, we are questioning this. Right? So as I said, the answer is no. Okay, just I will check, change the thickness of the pen. I will come back. Okay, it seems to be thick. I am not getting it properly, right? So the example is, take G equal to GL to R, that is 2 by 2 invertible real matrices. We know it's a group, right? Now start with an element A. Okay, I don't remember offhand. So the element is 0, minus 1, 1, 0, and B is 0, 1, minus 1, minus 1. Okay, square bracket is same as a ordinary bracket. Okay, you can check A squared is identity, therefore order of A is 2. And you can see B power 4 is identity, and then you can check order of B is 4. But what is AB? AB you will find it is going to be 1, 1, 0, 1. Therefore AB power n will be 1n 0, 1. Okay, therefore order of AB is infinite. So pause, review, proceed. Okay, but so this is the first result for today. Okay, now the second result we want to do is, suppose assume further. What does it mean? Our assumptions are the same as the first example. A, B are elements of G, and order of A equal to m, and order of B equal to n, and both are finite, and assume further A, B equal to BA. They commute. Then what is AB power m? AB power mn, that will be AB power mn into B power mn. a to the power mn, and this is a to the power m whole to the power n and b to the power n whole to the power m by law of exponents, which is identity power n, identity power m, which is identity times identity, which is identity. Therefore, AB is a finite order. Okay, so order of AB, we know it will be less than or equal to mn. In fact, order of AB must be a divisor of mn. This also we know earlier. Remember that? Okay, right. What is the result I am using? Suppose order of A is n and a to the power m is identity, then n divides m. This is the result I am using. Already seen. Okay, right. Now I hope all of you know how to prove this. Okay, the proof is, first thing is we prove if AB equal to BA, then A B power n is B power n A for all n in Z, but in particular for n in A. Okay, so how do I prove that? When n equal to 1, this is the assumption. Assume the result for n equal to n, let us prove for n plus 1. So this is going to be A B, okay, or n into B, right? But AB, this is AB power n into B, as I am using associate law. Therefore, it's Bn into A, B. But this is equal to Bn into AB. But since they commute, it is Bn into B, A. But that is Bn B, A. Therefore, B power n plus 1, A. Right? Therefore, by induction, this result follows. So, pause, review, proceed. And now you want to prove AB power n is A power n, B power n if A and B commute. For n equal to 1, the result is nothing. Okay, this is all right. So assume the result for n, then AB power n plus 1 will be, by definition, this is AB power n into AB. Remember, how did you define A power n? A power 0 is identity, A power 1 is A, and assume A power n is defined, then A power n plus 1 was A power n times A. Okay, that's what I am using. But this one, by induction hypothesis, is A power n, B power n, AB. Right? So now I can use associative law, therefore it's A power n, B power n A into B. By 1, this is by 1. This is A power n, A, B power n, B. Again associative law, A power n, A, B power n, B is A power n plus 1, B power n plus 1. Okay. So, pause, review, proceed. So this is essentially mainly for BSc students. Some certain things you will simply assume. You may not have seen a proof. Okay, that's why it also gives an experience how to deal with this kind of arguments. Okay, now let's go back. So order of A is m, order of B is n, and AB equal to BA, that is A and B commute. Then we saw the element AB is of finite order. Now you can ask what happens to BA. Okay, right? That is also very interesting. One can prove order of AB is same as order of BA. Right? Therefore, if AB is of finite order, BA will also be finite order. I will prove it, okay, and come back. So as I said, there are many results about thing which I want to do. Okay. Let me go back to, okay. So suppose G is an element of J and A is an element of G, then I am claiming order of AG, A inverse is order of G. If G is of finite order, then order of AG, A inverse is also finite. Okay. If this is of infinite order, This element is also infinite order. That's a statement. This AG A inverse is called conjugate of G by the group element A. Okay, that means conjugates are all have the same order. That's a loose way of saying. Now, how do I prove that? So, let us assume that order of G is finite to start with. Okay, then I will prove order of AG A inverse is also n. Okay, how do I prove that? So, the interesting thing is I want to know what is this good here. This is A G power n A inverse. Okay, this is what we want to prove. This is our claim. Okay, again by induction you prove it. N equal to 1. Okay, so let us prove that I have proved it for n, then I want to prove it for n plus 1. This is AG A inverse to the power n into AG A inverse. But this by induction, this is A G power n A inverse into A G A inverse. Therefore, these two get cancelled. Right? Therefore, what do I get? I get A G power n G A inverse, which is A G power n plus 1 A inverse. Therefore, the result is proved. Yeah? Proved. So, pause, review, proceed. Now, therefore, if order of G is n, then AG A inverse, AG A inverse to the power n is AG power n A inverse, that is A identity A inverse, that is identity. Therefore, order of AG A inverse is less than or equal to n. But notice that AG A inverse is a conjugate. Okay. So, what did you prove? Conjugate of G, order of this, conjugate of this is less than or equal to order of G. This is what you proved. Is that clear? Right? But notice that I can do this. G itself is a conjugate A G A inverse. Why? Because G I can write as A inverse A G, call this as X. Okay, I claim G is a conjugate of X. That means I have to write A inverse X A. What is A? Because by therefore this is A inverse A G A inverse A, that is equal to G. Right? Therefore, G is a conjugate of AG A inverse by the group element, by the element A inverse. So, for whatever be the element, we proved it. Therefore, order of G must be less than or equal to order of AG A inverse, but that's less than or equal to order of G. Therefore, equality holds everywhere. Pause, review, proceed. Okay. Right. Now I am ready to prove. Okay. Suppose this is finite. Suppose it's infinite order. Suppose it's infinite order. Suppose order of G is infinite. Then what will be order of? Let's look at, suppose order of AG A inverse for some A is finite. Right. But then we know that order of this is same as order of G, because G is a conjugate of AG A inverse. Therefore, the orders are the same. That's a contradiction. Right? Therefore, what have you proved? Whatever be the order of G, we have proved that, okay, for every A, order of G is same as order of AG A inverse. Is that clear? Pause, review, proceed. So now let's look at this is the result 4. Now let's look at the result 5. Suppose A, B are elements in G, and let's look at AB and BA. I want to say order of AB is same as order of BA. Why that follows? That's because AB and BA are conjugates. When I say conjugates, what does it mean? There is an element C, so that CA B C inverse will be BA, or there is an element D, so that D BA D inverse equal to AB. Okay. So what do I want? I want to look for a C, so that CA C inverse should be equal to BA. Right? So that is very clear. So I want CA, if I make it identity, yeah, I should be able to get. So if I want to make CA to be identity, what is my choice? C must be A inverse. So let us take C equal to A inverse AB, and what is C inverse? C inverse is A, right? So this is the conjugate, right? This conjugate is nothing other than BA. You follow that? So therefore order of AB is order of BA. It follows from 4. So pause, review, proceed. Okay. Therefore, now let's go back to what we proved. A and B are elements of finite order. Let us say orders are M and N. Then we proved order of A and assume that AB commutes. That is AB equal to BA, A and B commute. Then order of AB is also finite. It's at most M times N. The order is at most M times N. So what will be our gut feeling now? So remember, AB to the power Mn is identity. That means if suppose K is the order of AB, then K must be divisor of Mn. Right? So what do you think? See, when I was a student, my guess would have been the order of AB must be the least common multiple. Right? Okay. But that is not true. Are you following what I'm saying? Yeah. Remember, AB to the power L, okay, I will just go to screen share and do that. Okay. A guess, so let me, this is the point number 6. Okay. This is a dangerous thing. 6. Okay. Let L equal to LCM of M and N. What are our assumptions? AB equal to BA, order of A is M, order of B is N. Okay. Then we know AB to the power Mn is identity. Let us look at AB power L. That is also A to the power L into B to the power L. But A to the power L is A into some multiple of M, right? And B into some multiple of N. Therefore, each is identity, right? So, answer is no. Easy example actually does the job. Okay. What is the easy example? Suppose take A, okay, and take B equal to A inverse. Then what is AB? AB is identity. What is the order of AB? Is 1. But A could be of any order, right? A could be of any order. And we also know order of A is same as order of A inverse. Therefore, this could be anything. It could be finite, it could be infinite, right? For example, if the order is even if it's a finite order, the order of N, order of A is N, order of A inverse is N, then LCM is going to be n only. Least common multiple is n. But it need not be. It is identity, right? It could be any integer. Do you follow that? So that is not true. Okay. The next thing what we can do is something better. Okay. I thought this is the sixth one. The next thing is the interesting one. Suppose the same thing A, B are elements of G, order of A equal to P, order of B equal to Q, and let's assume P and Q are relatively prime. Okay. I am not assuming they are okay. When you see P, you will think P is a prime. No. P and Q are not prime. There could be any integers except their GCD is 1. That is P and Q are relatively prime. Then order of AB is PQ. This is a fantastic result. See, after so many negative results, you have something very concrete result. Okay, we will come back to the result often in this lecture. Okay, that first notice that AB power Q, AB power PQ is A power PQ and B power PQ, as we have seen earlier. AB power Q plus BQ to the power P, therefore it's identity. Therefore, okay, that's fine. Okay, now suppose order of PQ is n. So AB is a finite order. This we had already seen even earlier. Okay, right? Therefore, we know PQ, n must divide PQ. Right? Okay. Now we want to show n equal to PQ. Right? Right. Now the interesting thing I want to show is P actually divides n and Q divides n, and since P and Q are relatively prime, this would imply PQ divides n. Therefore, n divides PQ, PQ divides n, that will give me n equal to PQ. Okay, this is the result from element number theory. Okay, if time permits, I will come back to a proof of this. Is the proof clear? Is the idea clear? So, I want to say, therefore, we want to show P divides n and similarly Q divides n. This will be the same proof, so we will leave it. Okay, I want to say P divides n. Now, how do I prove that? Let us look at. So, I know AB power n is identity. That is A power n into B power n. So, this implies A to the power n equal to B to the power minus n. Right? Now, raise this to the power Q. What do I get? Then I get an to the power Q equal to B minus n Q, which is B power Q into minus n, which is identity. Is that clear? Therefore, A to the power nq is identity, but P is the order of A should divide nq. Right? Now, again we need a result from elementary number theory. What does it say? If P, a number, divides AB and GCD of P and A equal to 1, this will imply P divides B. Okay, this is another result from elementary theory. We will give a proof. Is that okay? Now let's go back. So now P divides NQ, but P and Q are relatively prime. Therefore, this implies P divides N. Similarly, You know, I want you to work it out. Similarly, Q divides N. And hence, by this result, elementary result 1, call it 1, and elementary result 2, call it 2. So, ENT1, this is Q. ENT1 implies PQ divides N. Therefore, we conclude PQ equal to N. Okay. Pause, review, proceed. Right. So, do you realize why before group theory I requested all of you to watch the videos on elementary number theory? Yeah, you can see you just can't live without it. Okay, right. Please go through some of the things I may not have done, but I will do it here. But please go through ENT completely. I will add few more lectures later. You will go through them. So let us go to proof of. This is the eighth result, which is not group theory result, ancillary result. Okay. What did you want to do? ENT1. What does it say? If P divides AB and P and A are relatively prime, okay, this implies P divides B, right? Okay. What should be the basic idea? Remember, I told you whenever there is a GCD and relatively prime comes, what is the most important result? How many of you remember? That is B's identity. Right? So what does it say here? That since GCD of P and A, therefore there exists integers U, V and Z, so that UP plus VA equal to 1. Right? Now I wanted to say P divides B. Where am I going to get B? There is no B here. So how will I get it? Multiply this equation by B. Then what do I get? I get U P B plus V A B equal to B. Is that okay? Right. Now notice that what you to notice is P divides this, right? Because there is a B. And by assumption P divides AB, therefore P divides this, right? Therefore P divides this. Is the proof clear? Yeah. So P or P. Okay. Now let's go to ENT2. What did it say? I hope that is ENT2. Oh, that is ENT2. Sorry. I'm very sorry. Yeah, that's ENT2. Sorry, this is what I proved is ENT2. Okay. What I want to prove is ENT1 now. What does it say? If GCD of P and Q is 1 and P divides N, Q divides N, that should imply PQ divides N. Is that clear? Yeah. So how do I prove this? Okay. Now P divides N, therefore I can write N as some M times P. Right? Since P divides N, I can write it. Therefore, now let us look at N is M times P and Q divides N, that means Q divides MP. Right? But Q and P are relatively prime, therefore by ENT2, in fact it would have been ENT1, so that it will be nice. By ENT1, Q must divide M. Yeah? So I write M equal to K times Q. Therefore my N equal to M times P, but M is K times Q times P, therefore PQ divides N. Isn't it easy? Yeah. It's unfortunately, many people don't realize the power of Bezo identity. Okay. Throughout algebra, later also it will come when you go to ring theory. Okay. It's better. That's why it's better to give a name so that you can simply recall it. Okay. Use it. Okay. Is that clear? Right. So what have we proved now? We proved some important result. If A and B commute and the A and B are of finite order, if their orders are relatively prime, then we said that order of AB itself is PQ, product of the orders. Is that clear? Very good. Now let's go back. What was our earlier guess? If A is of A and B commute, order of A is M, order of B is N, then I know AB is of finite order, then our guess was perhaps order of AB is LCM of M and N. Okay. As I said, that's not true, but there is something else which is true, and it is something very interesting. What is that result? See that. Let us see. This is the next result. G is a group. A, B are elements of G. A, B equal to BA, and order of A equal to M, order of B equal to N. Okay. Let L equal to LCM of M and N. Then there exists a C, a group element C in G, such that order of C is L. Please compare this result with the last one. The last one said if M and N are relatively prime, okay, this theorem, this result 10, what will it say? If M and N are relatively prime, it says there exists some C such that order of C is Mn. But the last result said that C you don't have to search for, it is actually the product AB. Yeah? Are you following? Here, I am not saying that AB will have order the LCM of M and N, but I am saying there exists some element. Please understand, this is the kind of subtlety one has to understand. People always are worried about proofs, etc., but you should also understand the statements properly, the subtleties should be appreciated. Okay. So, what we do is suppose D is the GCD of M and N, right? So, the idea is to reduce this problem to the earlier result. That is, I will find A is of order M, now I will find another element whose order is relatively prime to M and then do it. The idea is very clear, very simple. Let us do that. I hope I'm screen sharing. Yeah. Okay. Now notice that the basic result, again elementary number theory, you know this. Okay. A times B is nothing other than L times D. Here where L is the GCD and this. Right? Therefore, A by B by, sorry, right, for any number, so let me write M times N. AB is not group element here, M times N. Therefore, N by D will be L times D. Remember, D is a greatest common divisor, therefore N by D will be an integer. Right? Okay. So, what I want to do is, now notice that, what is the GCD of M and N by D? That is 1. Right? This also we have seen. Correct? Okay. So, now, are you clear about this? Because UM plus Vn equal to D divided by D, therefore U by D, okay, sorry. No, I don't want that. Okay. Right, let's come back. This way also it's the ENT. We must have seen it. We will come back to it later. So now what I want to do is I take A I take now the power of b, bd, and since a and b commute, we know a and bd also commute. And what is order of a? It is m. What is order of b? From our knowledge about cyclic groups, etc., we know the order of b is n, therefore the order of bd is n by d. Call it k if you want. Okay, write n equal to k times b. Is it okay? Right? Therefore, what do I know? Now, these two orders are relatively prime and they commute. Therefore, the order of a b power d is m into k. But m into k is the LCM. M into k is the least common multiple, because what do I have? M times n is L times d, therefore m times n by d is L. Okay, therefore take C equal to a b power d, then order of C is LCM of order of a, order of b. Is that okay? Right. Now think for a minute. We have got a proof, etc. is fine. What does the result say? Suppose my group G is abelian, right? And then any two elements will commute. Let me assume that the group G is finite and abelian, right? Then what does it say? Whenever you give me two elements A and B, okay, of order m and n, I can find element C whose order will be the LCM of m and n. Intuitively, do you see that? The C's order may be greater than or equal to m as well as n, because it's the least common multiple of m and n. Are you following? Sure. That can I keep doing? It seems to I can find an element of bigger order. Do you think this can happen? Please think. These kind of vague questions are the one you should learn to think. What does it say then? If G is a finite group, each of the element is a finite order, we had already seen. Right? Now, therefore, there is a maximum element whose order is a maximum. Right? Are you following? Something interesting. Okay? Maybe you are confusing. You are confused. Let me share the screen and explain. Okay, this is application 12, 11. This is an application of the earlier result. Okay, suppose G is finite and abelian. Okay, at present I don't need abelian, but it's finite. Therefore, let A in G be the order of A equal to maximum of order of G as G varies over G. This is the finite set of numbers. Therefore, the maximum exists. Okay, there exists at least one element whose order is maximum, right? Now, suppose it's abelian. Now you start with any B in G, right? Okay, then there I can always find an element C, so that order of C is the LCM of order of A and order of B, right? But this will be greater than or equal to order of A because it's a, right? Are you following? Okay, that means since A is the maximum, the order of A is the maximum number, this must be equal to order of A. Right? That means the LCM of order of A and order of B is order of A for every B in G. So what does it say about order of B? I have two numbers. Okay, this is the very easy things. Suppose I forget this m and n. Suppose m and n are natural numbers, and LCM of m and n is, let us say, m. What does it mean? That means n must be a divisor of m. Yeah? Are you following? Therefore, in this case, for every b, g in G, order of G divides order of B. Isn't it a beautiful result? If G is a finite abelian group, I can all find and consider any element which is of maximum order. Then order of any element will be the divisor of this maximum order. Yeah, it has a beautiful application in field theory. We will come to it later. Okay, right. Now the last result. Okay, is also very interesting. What does the last result say? Look at that. We said two elements of finite order. Then I cannot say anything about the order of AB. Right? It could be infinite. And the next thing is, if A and B also commute, then also I cannot say order of AB. Right? My guess may be it's LCM, but it's not true. But what we proved was, if order of A and order of B are m and n, if m and n are relatively prime, then order of AB is m times n. Very good. The next result said, okay, if m and n, the order of A is m, order of B is n, A and B commute, then there is an element C whose order is the LCM of m and n. Right? Okay. Now let's look at the symmetry group on n symbol Sn. It's highly, starting from n equal to 3 onwards, it's highly non-commutative group. Right? It's not a abelian group. But there is something very interesting happening there. What have we seen? If suppose sigma is a cycle of length k, we had already seen order of sigma is k. That is the length of the cycle. Yes? Very good. Number one. Number two. If sigma is any permutation in Sn, then I can write sigma as sigma 1 times sigma 2 times sigma r, where these sigma 1, sigma 2, sigma r are pairwise disjoint cycles. Correct? And hence they commute with each other. Because we already know disjoint cycles commute with each other. Therefore, they commute with each other. Right? Suppose the length are n1, n2, nr. Yeah? Now, the fantastic result says order of sigma is LCM of n1, n2, nr. I am going to write it. Please understand the statement. It's a fantastic result. This is the 12th one. Okay, I am considering Sn. Sigma is a cycle. Then length of sigma is, let's say, k. Then order of sigma is k. This we know. Already seen. Right? Okay. Now, suppose sigma is some arbitrary element Sn, and sigma I write as sigma 1 to sigma r, where this is called cycle decomposition. This is a pair, that means sigma I, sigma i's are pairwise disjoint. Pairwise disjoint. Right? The result we want to prove is order of sigma is LCM of, okay, length of sigma 1 and length of sigma r. Call this n1, nr. Therefore, it's LCM of n1 to nr. Okay, call this least common multiple as m. Okay, this is what we want to prove. Actually, we shall show, we are not showing. Okay. So before going to the proof, let's try to understand a few things. Okay. Suppose this m, let us look at sigma power m is sigma 1 sigma r to the power m. Since pairwise, these are all pairwise disjoint, they commute. Therefore, we know this is sigma 1 to the power m, sigma r to the power m. But each m is a multiple of n1. Therefore, this will be identity. M is a multiple of nr. Therefore, this is also identity. Therefore, I get identity. Right? Is that clear? Right. So, if m is the least common multiple, then therefore order of sigma, say n, let order of sigma be n, then n divides m. Is that clear? Now, let us do that. What do we mean by these cycles are pairwise disjoint? It will be easier if I introduce some notation. This is not common, not standard. What I am going to say is not standard, what do you call, not standard definition. Okay. If sigma is a cycle, sigma is a cycle. Okay. The support of sigma I is what? Remember, sigma is a cycle. That means it is of the form some, okay, let us call it, since I already use I would use some j1 to jni, right? That means where are these things? j1 to jni, j1 to jni, they are all elements into 1 to n. Now what happens if k is in 1 to n and k is not any one of the j1 to jni? Okay, then sigma I of k will be k itself. Do you understand this? Right? Apart from this, if k is not any one of them, sigma I of k will be k because it's not here. Okay, k is here, but k is not any one of them. Is that okay? This is what I call support of y. This set j1 to jni is what I call support of sigma I. Right? The next thing is, suppose I take some other sigma. Okay, well, let us say sigma, I'm running out of notation. Let us say sigma alpha, where okay, alpha is 1 to r. Because remember, sigma is sigma 1 to sigma r. Let us take this sigma alpha, and alpha is not equal to the I. Then what will happen to sigma alpha of any j coming from here? That will be j itself, right? Whatever the j here, suppose j belong to this, then sigma alpha of j will be j, because the support of alpha and the support of sigma I, sorry, sigma alpha are disjoint, right? Therefore, say sigma alpha will not move j, it will map to j. Okay, please understand, this is very crucial to what we want to do, right? Okay, now what is that I want to prove? I want to prove that my m is n. N is the order of sigma. This m is LCM of n1 to nr, right? Okay, what we already know is n is a divisor of m. Oh, so yeah, n is the order divisor of m, because we proved sigma power m is identity. Therefore, n must be a divisor of m. Okay. So the way I want to prove is, I want to prove, okay, m divides n. Okay. How I want to prove that? I will show that, okay, we claim each ni divides n. That means n is a common multiple. Ni, right? But what is m? M is the least common multiple. Right? Since m divides n, that means m is less than or equal to n, but m is the least common multiple, but n is the common multiple, therefore m should be, sorry, n divides m, therefore n is less than or equal to m. Sorry, I go back. Okay. What we proved was sigma power m is identity, where n is the order, therefore n must divide m, that means n is less than or equal to m. Okay. Now we are saying each ni divides m, that means n is a common multiple of ni, but m is the least common multiple, therefore m should be less than or equal to n. Okay. So let us look at these two results. Okay. Therefore we will prove that m equal to n. Okay. Understand this? Okay. Don't give up. We are near the end. Okay. Yeah. Now let us look at what do I know is sigma power n is identity. Right. Now let k be any element into 1 to n. Right. So to show n ni divides n, I will show that sigma I power n is identity. Right. But ni is the order of sigma, therefore the order of sigma I, which is ni, must divide n. Do you follow that? So what we want to prove is, therefore enough to show sigma I power n is identity. Okay. So let us go through the proof. Now start with any k in 1 to n. Right. Suppose k is not in support of sigma I, then sigma I of k is k. Therefore sigma I power n of k is also k. Right. Therefore, okay. So the way we want to prove is, I want to prove sigma I power n is identity. Therefore I will prove sigma I power n of k is k for every k in this set, because it's a permutation, right? I want to say it's identity permutation. Is that okay? So if k is not in the support of sigma I, then sigma I of k is k. Therefore sigma I power k, sigma I power n of k is k. So the result is true. We proved this result for k not equal to. Now suppose k is in support sigma I, right? Then let us see. Then what I have is k is identity of k, but this is sigma power n of k. Remember, n is the order of sigma. But what is this? This is sigma 1 power n. Okay, composite sigma r power n, this acting on k. Right. Now since k is in the support sigma I, just assume r equal to 2 to make the idea clear for you. Let me just do it. Sigma 1 to the power n, sigma 2 to the power n. Let me assume k is in the support of sigma 1 to make understand, right? Therefore this acting on k. Remember, sigma k is in the support of sigma 1 and therefore k is not in the support of sigma 2. Therefore sigma 2 of k will be k. Therefore this will be k. Therefore sigma 1 power n of k. So I proved sigma 1 of power k equal to k. Is that clear? Okay, pause. Review, proceed. So now general case let us look at. Therefore K equal to identity of K equal to sigma n of K equal to sigma 1 power n sigma r power n, this acting on K. And where is K? K is supposed to be in the support of sigma I. Therefore what will happen is, up to this, okay, each one of them will return K only. Therefore I have sigma I power n of K, right? But where does it belong to? This element will belong to a support of sigma I, right? Therefore starting from here, all the elements will not touch it. They will, you understand this? Suppose I have sigma I minus 1 power n, okay, that acting on sigma I power n of K, this belong to support and it does not belong to support of sigma I minus 1, therefore it will leave untouched. So what finally I get will be, the final result will be sigma I power n of K. So we have proved for all I, sigma I power n of K is K, for all K is equal to n. Therefore what it follows is Ni divides n, right? As I said, therefore n is a common multiple. Ni and m is the least common multiple. Therefore m must be less than or equal to n. We already know n is less than or equal to m because sigma power m is identity. Therefore n divides m. Therefore we know that n is less than or equal to m. Therefore n equal to m. So again I made the mistake as usual. Yeah, I forgot to share the screen. Okay, I'm sorry. We'll go back. I'll do it quickly. Since I have already written, I will explain. Okay. So the trick is, we will show that each Ni divides n. The way I want to show this is, I will show sigma I put to the power n is identity, right? That means order of sigma I, which is Ni, must be a divisor of n. Now to show sigma I power n of identity, that sigma I power n is again a bijection of 1 to n, right? To show this is the identity bijection, that is identity permutation, that means sigma I power n of K equal to K for all K into 1 to n. This is all I have to prove, right? So the way I prove is, suppose K is not in the support of sigma I, then sigma I of K is K, therefore sigma I power n K is K. Therefore that result is proved if K is not in the support. Okay. Now suppose K is in the support. Okay. Then let us look at K is identity acting on K, but that is sigma power n acting on K, but that is equal to sigma 1 composite sigma n sigma r to the power n K, right? So to explain the idea, I assume r equal to 2. Then it is going to be sigma 1 to the power n, sigma 2 to the power n. Again, to explain the idea, let me take I equal to 1. Therefore it's sigma 1, right? Now K is not in the support. Sorry, K is in the support of sigma 1. Since K is in the support of sigma 1, K is not in the support of sigma 2. Therefore sigma 2 acting on K will be K. Therefore sigma 2 power n K will be K. Therefore what I get is sigma 1 power n K, that is equal to K. Therefore we proved when K is in the support. So for general OR, the way I did this is something interesting. So look at this, K equal to identity of K equal to sigma n power K, this etc. Now up to this, okay, K is in the support of sigma I, therefore K is not in the support of sigma r minus 1, sigma I plus 1, right? Therefore each one of them, when acting upon this, that will return K, the next one will also return K, up to this one will return K. So I get finally here, I will have sigma 1 power n, etc., sigma I minus 1 power n and sigma I power n K. Is that okay? But sigma, now see, this is a cycle, therefore sigma I power n K will be in the support of sigma I, right? But So this element, when it's fed to this cycle, okay, this element is in the support of sigma I, therefore it's not in the support of sigma I minus 1, therefore it will leave this element the same. Okay, therefore sigma I minus 1 power n of sigma I power n of k will be equal to sigma I power n of k. So this will keep doing the same way. So final result is this object is nothing other than sigma I power n k. Therefore we have proved sigma I power n k equal to k if k is in support of sigma I. Okay, that proves the result. So I know it has been highly demanding thing. So this is meant for essentially, I would say, MSc students, and that too students who are keen to uh, pursue algebra. Okay, but all these things are very good. If you want to be an algebraist, this will be very good. And those of you who are BSc students, I hope if you struggle, discuss with your friends. Okay, you will see that you will enjoy algebra later. Okay, I hope you enjoyed. Thank you very much. We will meet again.